Today, I'll introduce rational exponents. First, let me review the different kinds of numbers. We have the integers, which are the whole numbers like 0, 1, 2, but we also have negative integers too, right? So we have -1, -2, and on and on and on that way, on and on and on. The set of integers is the set of all whole numbers going from -infinity to infinity. A rational number which is what we'll be working with today, is a number that can be written as m divided by n, where m and n are both integers. So a rational number is a fraction of whole numbers, like 1/2, 3/4, 77 over 223. Any number that can be written like this is rational. So maybe I have a number like 3.5 divided by 7.46. That's not in rational form, but it is a rational number because I can multiply this by 100 over 100, and that's 350 over 746, and that's clearly rational. Irrational numbers are numbers that can't be written m divided by n, where m and n are integers. These are numbers like pi, which is a circle's circumference divided by its diameter. E, which is used in exponential growth, it's 2.718 something. Two other common ones are the square root of 2 and the square root of 3. There's no formula for how to get irrational numbers, and it's difficult to prove that numbers are irrational. I think discovering them is still an area of active research in mathematics. The real numbers are the collection of rational numbers and irrational numbers. Note that any integer is a rational number because it can be written as a fraction with 1 in the denominator. Like 3 is a rational number because it can be written as 3 divided by 1, and that's m divided by n, where both are integers. If we diagram the real numbers, they look like this. They're split into rational and irrational because a number can't be both, and the integers are included in the rational section. And I believe that there are actually more irrationals than rationals. I think that's something that's been proven. Later in the class, we will briefly get into complex numbers where we take the square root of a negative number, and it turns out that all real numbers can be written as complex numbers. So there's a bigger set of numbers that contains this set of real numbers. Today, we want to get into rational exponents. The way it works is we have a to the m divided by n. The denominator is the power of the root you take, and the numerator is the power you raise it to. You've probably seen this notation before, square root a. This refers to the positive square root of a. So if we wanted both square roots, we would write plus or minus square root a. Square root a equals b, where b squared equals a, and b is positive. So square root of 49 equals 7. Square root of 16 equals 4, etc. To write this as a rational exponent, we would write a to the 1/2. This says take the square root of a, and that would be plus or minus b. So it refers to either the positive or negative square root. But we won't worry about that today. The important thing for today is that we're taking the second root and raising it to the first power. A to the 1/3 would be the cube root of a. If a to the 1/3 equals b, then b cubed equals a. So for example, 27 to the 1/3 would be 3, because 3 cubed equals 27. We're taking the third root. If the numerator is not 1, then we have to raise the root to that power. So if I want 27 to the 2/3, that means take the third root and square it. It doesn't matter what order you do this in. I could find 27 squared, which is 729, and then take the cube root of that, and that gives me 9. Or I could take 27 to the 1/3, which is 3, and square that, and that will also give me 9. Like I said, the order here doesn't matter. Let's try another. What is 625 to the 3/4? Well, 625 to the 1/4 is 5, and then we would cube that to get 125. We could also find 625 cubed and then raise this to the 4th power. 125 again. All the rules that we learned for integer exponents apply to rational exponents, of course. The product rule if we have the same base and we multiply two of these expressions, we add the exponents together. So 3 to the 1/3 times 3 to the 4/3 equals 3 to the 1/3 plus 4/3, and that's 3 to the 5/3. That would be the third root, or the cube root, of 3 to the 5th power. Remember that to add fractions, you need a common denominator. 6 to the 4/5 times 6 to the 2/3 would be 6 to the 4/5 plus 2/3. The common denominator for 5 and 3 will be 15. So I would want 4/5 times 3 divided by 3, and that's 12 over 15. And 2/3 times 5 over 5, and that's 10 over 15. So what I would get is 6 to the 12/15 plus 10/15, and that's 6 to the 22/15. And that would be the 15th root of 6 to the 22nd power. The quotient rule says to subtract exponents when you divide. And that's the same thing. You need to have a common denominator. 4 to the 3/4 divided by 4 to the 1/6 equals 4 to the 3/4 minus 1/6. The common denominator for 4 and 6 is 12. That would be 3/4 times 3, 3. And 1/6 times 2, 2. Four to the 7/12. And that's the 12th root of 4 raised to the 7th power. The power rule says a to the m to the nth power equals a to the m times n. And remember, when multiplying fractions, you multiply the numerator times the numerator and the denominator times the denominator. For example, a divided by b times c divided by d equals ac over bd. An example, 7 to the 2/3 to the 5/7 power would be 7 to the 2/3 times 5/7, and that equals 7 to the 10 over 21. The 21st root of 7 to the 10th power. The negative exponent rule works exactly the same. The negative exponent is always 1 divided by the positive exponent. Five to the negative 1/4 is the same as 1 divided by 5 to the 1/4. And the zero exponent rule doesn't change at all. 0 is a rational number. A to the 0 equals 1 no matter what A is. There aren't any fractions or roots to deal with here.